So everything that has to do with refrigeration and air conditioning is done by vapor compression technology, where this chemical refrigerant called hydrofluorocarbon, it absorbs and releases latent heat. Except the problem is that hydrofluorocarbon, it's contributing significantly to the global warming problem. And that's why we started thinking that we can make cooling devices by stretching nickel titanium wire. So we stretch it, and it actually releases heat. And you unstretch, it's cooling its surrounding. But it hadn't been a prevalent phenomenon that was well known. So when we first approached Department of Energy, they said, as far as we know, no such phenomenon exists. And so that's when we said, exactly, you should let us try it. My name is Ichiro Takeuchi. I study material science and engineering at the University of Maryland. We try to discover new functional materials, and we also try to come up with new applications for them. This material, this shape memory alloy, especially nickel titanium, never stops surprising us. Shape memory alloys have these special properties. So by stretching it, it's essentially going from one crystalline structure to another. And in doing so, it necessarily has to give off heat associated with the transformation. But in turn, when you change the temperature of the surrounding of the alloy, it goes back to the original shape and structure at the atomic level, and it has to absorb heat. And when the material absorbs heat, it's cooling its surrounding. Except sometimes atoms could get stuck and it starts producing defects. So the more cycles you operate these materials, the more and more defects could pile up. And eventually that's what leads to a failure. So initially, 10, 12 years ago, we were able to actually make materials where the high temperature and the low temperature have a compatibility in the crystal structure. And we were able to test that indeed the fatigue life is long. And that's when we discovered that it could exhibit a really large cooling and a heating effect, something like 30 degrees Fahrenheit. So we started thinking that we can make cooling devices out of this. And that's sort of how we got into this field. So we started the project making simple toy devices with stretching a strand of wires together. And then we slowly started moving toward large-scale devices. Ended up taking us 10 years, and there's a lot of really tricky engineering that went on. It turns out compression doesn't lead to as much fatigue as in the tension case. So we have hydraulic actuators that pushes on the shape memory alloy, which is held at the other end, and that's how it gets compressed. At the same time, we discovered that cooling air directly is an extremely inefficient process. And that's why now we use water. During every cycle, we need to have water, have it back and forth in the device. But as long as you load it in the right configuration, it could survive more than 10 million cycles. Those are important numbers because if you think about buying an air conditioner, that immediately translates to tens of millions of cycles. So we designed this rig in such a way so that we could test that, and at the same time, we could observe large temperature change. And right now, we've demonstrated a cooling device with sufficient power so that now one can begin to think about real applications. So there are different directions that we're pushing this technology. As long as we're working on nickel titanium, the force or the stress is simply too large. And in some instances, it requires hydraulics. And they're pretty inefficient. If you want to make a viable commercial product, I believe we need to switch to a different material. And it turns out there are a variety of other shape memory alloys. So one type is a copper-based shape memory alloys, some of which requires a lot smaller stress. We hope at that level, it's as efficient as the vapor compression. Climate change is real. Countries are taking on the challenge. But realistically, vapor compression will survive. What we can hope for, there will be niche applications. something like wine fridge. Perhaps we could use this for medical fields where, people have to transport organs and other things cooled in a small package. But, that's a start. And whatever we can do to reduce emission of hydrofluorocarbons, we need to do.